We'll now look at the Euler Approximation Method for finding solutions to differential equations. So what we need to do this method is a first-order initial value problem. So we need a differential equation that's of the form y prime equal to some function involving x and y. And then we need an initial point, y of x0 equal to y0. So let's start with kind of the general idea. We're going to start at the initial point x0, y0, and this is going to be a graphing method, so go ahead and plot that point. The next step, we follow the straight line with slope f of x0, y0 to the point x1, y1. So essentially, we're going to determine the slope of the tangent line at the point x0, y0, and essentially just draw a short segment of that tangent line. The point x1, y1 just kind of depends on how big you want to make your steps, but essentially just follow along that tangent line for some amount of time. You then use your differential equation to find the value f of x1, y1, and let that be the new slope and continue to the point x2, y2. And essentially you just kind of continue this basic process of finding slopes and drawing these little small lines. So let's look at kind of the idea of it. So here's a very, very basic example. Down at the bottom left, I have the point x0, y0. I use my differential equation to find f of x0, y0 and draw a line segment with that slope up to the point x1, y1. I then use my differential equation to find f of x1, y1 and draw a line segment with that slope up until the point x2, y2. I then use my differential equation to find f of x2, y2 and draw a little segment with slope of that until the point x3, y3, etc. So let's see if we can formalize this a little bit before we actually delve into examples. We're going to start by assuming our initial value problem does have a unique solution, denoted by phi of x, in some interval around our initial point x0. We're also going to let h be a fixed positive number. This is called the step size. We're going to define xn to be x0 plus nh, where n is the whole number 0, 1, 2, 3, etc. So these are going to be our x coordinates for our points in our Euler method. So now the question is, what about the points yn, and how does that approximate this actual solution, phi of x? At the point x0, y0, the slope of our solution is given by the derivative of y equal to f of x0, y0. So this is not an estimation. This is an actual point that we know lies on our solution. So this is the exact slope at that given point. So we're able to find an exact equation for the tangent line at that point. y0 plus x minus x0 times the slope. And we're going to use this to approximate our solution. So x1 is defined by x0 plus h. So we're going to define y1 by what happens whenever I stick x1 into this equation. So y1 would then be y0 plus, instead of x, I'm going to use x1, so x0 plus h, minus x0 times f of x0, y0. So we'll define y1 by y0 plus h, f of x0, y0. And you can continue this process. Start at the point x1, y1, find the equation of the tangent line, and then stick in the value of x2 into it. And continuing this process gives us this formula that yn plus 1 is defined as yn plus h times f of xn yn. We can also redefine our x's in this recursive formula form, where xn plus 1 is equal to xn plus h. So this is the general idea. This is how we find our points, x1, y1, x2, y2, x3, y3, etc. And then we just draw the line segments between these points, kind of like a connect the dots.